Look up at the night sky. Right now, at this very moment, there's a visitor moving through our cosmic neighborhood, a traveler that has journeyed for billions of years across the vast interstellar ocean, carrying secrets from a world we've never seen, from a star system we may never visit. Its name is 3I Atlas, and it has shattered nearly every assumption we've made about what comets should be. This is not just another space rock. This is not just another icy wanderer from the outer reaches of our solar system. This is something profoundly different, something that challenges the very foundations of what we thought we knew about the building blocks of planetary systems. And perhaps most remarkably, it has revealed a truth that sounds almost impossible when you first hear it. This comet, this ancient traveler from the depths of interstellar space, is not made of water. It's not a water comet. Let that sink in for a moment. For as long as humans have studied comets, we've understood them as cosmic snowballs, dirty icebergs tumbling through space, composed primarily of frozen water mixed with rock and dust. When they approach the sun, that water ice vaporizes, creating the spectacular tales that have inspired awe and sometimes terror throughout human history. Water has been the signature, the defining characteristic, the very essence of what makes a comet a comet. But 3I Atlas defies this ancient pattern. It is something else entirely. Discovered on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System telescope nestled in the Chilean mountains, 3I Atlas immediately caught astronomers' attention not because of what it was, but because of where it came from, its trajectory, its speed, the hyperbolic arc of its path through our solar system, all pointed to one stunning conclusion. This object had not been born here. It had not formed in the great disk of material that swirled around our infant sun 4.5 billion years ago. No, this visitor came from somewhere else entirely, from another star system, from a planetary construction zone we will likely never see. The designation itself tells a story. The number 3, because 3I Atlas is only the third confirmed interstellar object ever detected passing through our solar system. The letter I, standing for interstellar, marking it as an outsider, a cosmic foreigner, and Atlas, named for the survey that first spotted this remarkable wanderer. Before it, there had been only two others. The enigmatic Oumuamua in 2017, that strange, elongated object that blazed through our system and disappeared before we could study it properly. And 2I Borisov in 2019, which looked and behaved more like the comets we know, reassuring us that perhaps interstellar objects weren't so different after all. But 3I Atlas had other plans. It arrived to teach us humility, to remind us that the universe is far more diverse, far more creative, far more surprising than we can possibly imagine from our small vantage point on this pale blue dot. When astronomers first began observing 3I Atlas in earnest, they saw what they expected to see. There was a nucleus, the solid core of the comet, and surrounding it, a coma, that luminous halo of gas and dust that forms when a comet's ices begin to sublimate, turning directly from solid to gas as solar radiation heats the surface. This is standard comet behavior. This is what comets do. The sun's warmth causes the ices to vaporize. The released gases carry dust particles along with them, and together they form that characteristic fuzzy appearance that distinguishes comets from the sharp points of stars. But then came the spectroscopy, and with it, the revelation that would change everything. When you pass light from a celestial object through a prism or a spectrograph, you can break that light into its component wavelengths, creating a spectrum. And embedded in that spectrum, like a cosmic barcode, are the fingerprints of the elements and molecules present in that object. Every substance absorbs and emits light at specific wavelengths, creating a unique pattern that allows us to determine what something is made of, even from hundreds of millions of miles away. It's one of astronomy's most powerful tools, allowing us to touch the untouchable, to analyze worlds we could never physically reach. The James Webb Space Telescope, our most sophisticated eye in the sky, turned its gaze toward 3I Atlas on August 6, 2025, when the comet was still more than 3 astronomical units from the Sun, well beyond the orbit of Mars. What Webb saw in its near-infrared observations was unexpected, puzzling, and frankly, astonishing. The spectrum revealed carbon dioxide, lots and lots of carbon dioxide. CO2 gas was absolutely dominating the coma, pouring off the comet's nucleus at a rate of approximately 70 kilograms per second. For perspective, that's roughly the mass of an adult human being, vaporizing off this ancient icy world every single second. But here's where it gets truly remarkable. The water that astronomers expected to see, the water that should have been the primary volatile substance, the water that defines comets as we know them, was barely there. When scientists calculated the ratio, they found something that sits far outside the normal range. For every 8 molecules of carbon dioxide in the coma of 3I Atlas, there was only 1 molecule of water, 8 to 1. That's not just unusual, that's extraordinary. Most comets we've studied show the opposite trend, with water dominating and carbon dioxide playing a supporting role. In fact, the carbon dioxide to water ratio in 3I Atlas is one of the highest ever measured in any comet, sitting a full 6 standard deviations above what we typically observe. In the language of statistics, that means this isn't just rare. It's an outlier, an anomaly, something that demands explanation. To put this in perspective, imagine expecting to find an ocean and instead discovering a desert. That's the magnitude of the surprise. Only about 4% of the gas being released from 3I Atlas is water. 4%. The remaining 96% is dominated by carbon dioxide, with contributions from carbon monoxide and trace amounts of other molecules like carbonyl sulfide. This is not how comets are supposed to behave. This is not the recipe we've come to expect from billions of years of comet observation in our own solar system. The Spherex Space Observatory confirmed these findings, detecting a massive carbon dioxide gas cloud extending at least 348,000 kilometers from the nucleus. That's nearly the distance from the Earth to the Moon. This comet is wrapped in a vast cocoon of CO2, streaming away from its surface like a fire hose running at full blast, to use the evocative phrase one researcher employed. But unlike the fire hoses we know, this one is shooting carbon dioxide, not water. The question that immediately rises in any curious mind is simple and profound. Why? Why is this comet so different? What happened to create such an unusual composition? What does this tell us about the world where 3I Atlas was born? The answer, as it turns out, reaches billions of years into the past and spans the incomprehensible distances of interstellar space. Scientists have proposed several hypotheses, and the evidence suggests that the truth likely involves a combination of factors, each one revealing something fundamental about how planets, comets, and entire solar systems form. The first possibility takes us back to the birth of 3I Atlas, to a time when its home star was young, surrounded by a swirling disk of gas and dust, the raw material from which planets and comets would eventually coalesce. In these protoplanetary disks, temperature matters enormously. As you move farther from the central star, temperatures drop, and different substances begin to freeze out of the gas, forming solid ices. Close to the star, it's too hot for anything but rock and metal. A bit farther out, water ice can form. Even farther still, beyond what astronomers call the carbon dioxide ice line, CO2 begins to condense and freeze. It's quite possible that 3I Atlas formed in a distant, frigid region of its natal protoplanetary disk, far beyond the CO2 ice line, in a zone where carbon dioxide ice was naturally abundant compared to water ice. Different star systems, after all, have different chemistries, different abundances of elements, different temperature profiles in their planet-forming regions. Perhaps the planetary system where 3I Atlas was born simply had a composition that favored carbon dioxide over water in the icy bodies that formed in its outer reaches. This would make 3I Atlas a pristine sample of a very different kind of planetary construction environment, a frozen time capsule preserving the chemical signature of another star's planetary nursery. But there's a second factor, perhaps even more profound, that has almost certainly played a role in shaping 3I Atlas into what it is today, and that factor is radiation, specifically the relentless bombardment of galactic cosmic rays that pervades interstellar space. Here in our solar system, we're protected. The sun generates not just light and heat, but also a wind of charged particles, a stream of protons and electrons that flows outward in all directions, creating an enormous bubble called the heliosphere that extends far beyond the orbit of Pluto. This heliosphere acts as a shield, deflecting and weakening the cosmic rays that would otherwise bathe the inner solar system in high-energy radiation. We live in a cosmic safe haven, a bubble of relative calm in an otherwise harsh environment. But when you leave a solar system, when you venture into the true interstellar medium, that protection disappears. Out there in the space between the stars, there is no heliosphere, no shield, no shelter from the cosmic rays that streak through the galaxy at nearly the speed of light. These are particles accelerated to incredible energies by supernova explosions, by the churning magnetic fields around neutron stars and black holes, by processes we're still working to fully understand. And when these high-energy particles strike matter, they don't just bounce off. They penetrate deep, sometimes meters deep, and they change the very atoms they encounter. Over billions of years, this matters. Over the unimaginable spans of time that an object like 3I Atlas has been drifting through the galaxy, this radiation processing becomes profound. Recent research, combining observations from the James Webb Space Telescope with sophisticated computer simulations, has revealed what billions of years of cosmic ray bombardment can do to an icy body. When galactic cosmic rays strike molecules of carbon monoxide frozen in the ice, they have the energy to break chemical bonds and rearrange atoms. One of the products of this process is carbon dioxide. Slowly, over eons, CO in the ice gets converted to CO2 by radiation chemistry. And because this process penetrates deep into the object, down to depths of 15 to 20 meters or more, it doesn't just affect the surface. It transforms the comet throughout, creating what scientists call an irradiated crust, a layer of ice that has been fundamentally altered by its exposure to the harsh radiation environment of interstellar space. In the protected environment of our solar system, comets don't experience this kind of processing. They might spend billions of years in the Oort cloud, but they're shielded by the heliosphere. Their chemistry remains largely pristine, unchanged from the time of their formation. But an interstellar comet has no such protection. It spends most of its existence wandering through the galaxy, and during that time, it's being slowly, inexorably transformed by radiation. Computer models suggest that 3I Atlas has been on its interstellar journey for approximately 7 billion years. 7 billion years. To put that in perspective, that's longer than our own solar system has existed. When 3I Atlas first left its home star system, Earth didn't exist. The sun was younger. The universe itself was younger. And during all that time, during every single one of those 7 billion years, cosmic rays have been striking this frozen world, penetrating its ices, rearranging its molecules, slowly converting its carbon monoxide into carbon dioxide. One scientist involved in this research described it as a paradigm shift in how we understand interstellar objects. 3I Atlas, they realized, no longer truly represents the chemistry of its birth system. It has been transformed. The outer layers, at least, have been so thoroughly processed by radiation that they no longer resemble the original material. It's like finding an ancient artifact that has been weathered and changed by time until it bears little resemblance to its original form. 3I Atlas still contains valuable information, but we have to account for the fact that it has aged, that it has changed, that the galaxy itself has left its mark upon it. This realization is both humbling and exciting. It suggests that when we study interstellar objects, we're not just studying the chemistry of other planetary systems. We're also studying the effects of the interstellar medium itself, learning about the radiation environment between the stars, understanding how objects evolve during their long journeys through the galaxy. Each interstellar visitor becomes a dual messenger, carrying information both about its birthplace and about the journey it has taken to reach us. But the story of 3I Atlas doesn't end there. In fact, in some ways, it only gets more mysterious. As 3I Atlas approached the Sun, hurtling inward on its hyperbolic trajectory at speeds of nearly 60 kilometers per second, astronomers watched it closely, trying to predict how it would behave, what it would reveal. Comets typically become more active as they approach the Sun, releasing more gas and dust as solar heating intensifies. There are established patterns, well-understood behaviors that allow astronomers to make reasonably accurate predictions about how bright a comet will become, how large its coma will grow, what kind of tail it will develop. 3I Atlas, predictably, ignored these expectations. In the days and weeks before its closest approach to the Sun, which occurred on October 30th, 2025, the comet exhibited a series of behaviors that have left astronomers scratching their heads. It brightened more rapidly than anticipated, becoming significantly brighter than models predicted for a comet of its size and distance. Its color shifted in unexpected ways, appearing distinctly bluer than the Sun in certain observations, contrary to the reddish hue typically seen in comets as sunlight scatters through their dusty comas. These aren't the kinds of subtle variations that might go unnoticed. These are significant attention-grabbing anomalies. Perhaps most puzzling was the detection of non-gravitational acceleration. When a comet releases gas, that gas doesn't just drift away gently. It jets off the surface with some velocity, and in accordance with Newton's third law, for every action there's an equal and opposite reaction. The comet experiences a tiny push in the opposite direction. This is a well-known effect, and astronomers routinely account for it when calculating comet orbits. But the non-gravitational acceleration observed in 3I Atlas was unusually strong. Analysis of its trajectory showed that the comet was deviating from a purely gravitational path by a measurable amount. To produce the observed acceleration through normal outgassing would require the comet to lose more than 13% of its total mass during its passage around the Sun. 13%. That's an enormous amount of material to shed in such a short time. And if it did lose that much mass, there should be evidence. There should be a massive, obvious coma filled with dust and gas. There should be a prominent tail streaming away from the Sun. There should be clear, unambiguous signs of this tremendous activity. But when astronomers captured images of 3I Atlas after its perihelion passage, after it had rounded the Sun and begun its outward journey back toward interstellar space, those expected signs were remarkably subdued. The coma was there, certainly, but it didn't look dramatically different from how it had appeared months earlier when the comet was much farther from the Sun. There was no massive dust tail, no spectacular display of cometary fireworks. It was, to use the technical term, weird. Observations also revealed some unexpected chemical signatures. The Very Large Telescope in Chile detected unusually high levels of atomic nickel vapor in the coma, with a nickel-to-iron ratio that was far higher than typically seen in solar system comets. In most comets, nickel and iron appear together in roughly equal proportions, released from organometallic compounds that sublimate at relatively low temperatures. But 3I Atlas showed strong nickel emission and weak iron emission, at least initially. As it approached the Sun, This ratio began to normalize, suggesting that temperature-dependent processes were at work. But the initial imbalance was striking. Now, I need to address something here. Whenever an object behaves in unexpected ways, whenever the data don't quite fit the simple models, there are always those who will suggest that perhaps we're dealing with something other than a natural object. Perhaps, they speculate, this is artificial. Perhaps it's a probe sent by an extraterrestrial civilization. Perhaps the non-gravitational acceleration isn't from outgassing at all, but from some kind of propulsion system. These ideas, championed most notably by Harvard astrophysicist Avi Loeb, have generated considerable media attention and public interest. And I want to be very clear about something. Science thrives on questioning assumptions. It's good to ask unconventional questions. It's good to consider possibilities that might seem unlikely. That's how we avoid falling into the trap of thinking we know everything, of becoming so wedded to our models that we miss something genuinely new. And this is crucial, extraordinary claims require extraordinary evidence. And the evidence for 3I Atlas being anything other than a natural comet, while intriguing, is far from extraordinary. The overwhelming consensus among comet scientists, based on the full suite of observations from multiple telescopes, is that 3I Atlas is exactly what it appears to be, a comet. An unusual comet, certainly, a comet with properties that challenge our existing models and force us to expand our understanding. But a comet, nonetheless. The carbon dioxide, the water depletion, the unusual behavior near perihelion, all of these can be explained, at least in principle, by natural processes. Radiation processing over billions of years, formation in an unusual region of a protoplanetary disk, complex thermal properties that affect how different ices sublimate. The comet doesn't need to be artificial to be interesting. In fact, the natural explanations are, in many ways, more fascinating because they tell us about the diversity of planetary systems, about the effects of interstellar travel, about processes we're only beginning to understand. What 3I Atlas represents ultimately is an opportunity. It's a chance to study material from another stellar system without having to send a spacecraft across light years of distance. It's a cosmic gift, a sample delivery from the galaxy itself. And the fact that it's different from the comets we're familiar with isn't a problem to be explained away. It's the whole point. This is what we should expect. Different stars, different planetary disks, different formation conditions should produce different comets. The surprising thing would be if interstellar comets all looked exactly like the comets from our solar system. That would suggest something was deeply wrong with our understanding of planetary formation. Instead, what we're seeing is diversity. Oumuamua was unlike anything we'd seen before, potentially more asteroid-like than comet-like, though we still don't fully understand it. 2Y Borisov looked reassuringly familiar, but had an unusually high carbon monoxide content. And now 3I Atlas, with its carbon dioxide dominance and its water depletion, shows us yet another variant, another way that comets can be. This is the universe showing us its range, its creativity, the myriad ways that ice and rock and organic molecules can come together to form worlds. And we're only seeing the beginning. As our surveys improve, as our telescopes become more sensitive, we'll detect more of these interstellar visitors. Current estimates suggest that at any given time, there might be dozens or even hundreds of interstellar objects passing through the inner solar system, too faint to detect with current technology. Every few years we might spot one, and each one will teach us something new. The European Space Agency, recognizing the scientific value of these visitors, is developing a mission called Comet Interceptor, designed specifically to rendezvous with a newly discovered comet, ideally an interstellar one, or a long-period comet on its first pass through the inner solar system. The spacecraft will wait in space, ready to be deployed on short notice when a suitable target is found. Imagine that. A spacecraft sitting in orbit, patient, waiting for the next cosmic messenger to arrive, and then launching to intercept it, to fly alongside it, to study it up close with instruments far more sophisticated than any telescope on Earth or in orbit. When that happens, when we can analyze an interstellar comet not just from a distance, but from close range, when we can study its surface, measure its composition directly, watch its ices sublimate in real time, we'll learn things we can't even imagine yet. We'll answer questions we haven't thought to ask. But even now, even with just the remote observations we have of 3I Atlas, we're learning profound things. We're learning that planetary systems are more diverse than we thought. We're learning that the interstellar medium is not just empty space, but an active environment that shapes and transforms the objects that pass through it. We're learning that our models of comet composition need to be broader, more flexible, more capable of accommodating the full range of possibilities that nature can produce. And, perhaps most importantly, we're learning humility. We're being reminded once again that the universe is under no obligation to make sense to us. It doesn't have to fit our preconceptions. It doesn't have to behave the way we expect. It simply is what it is in all its strange and wonderful complexity, and our job as scientists, as explorers, as curious beings fortunate enough to live in an era when we can study these things is to observe, to measure, to question, and to try to understand. The story of 3I Atlas is still being written. As I speak these words, the comet is already on its way out of the solar system, heading back toward interstellar space. It will fade from view, becoming too dim to observe even with our most powerful telescopes. But the data we've collected, the images we've captured, the spectra we've analyzed, will keep scientists busy for years to come. Papers will be written, models will be refined, debates will continue about exactly what processes shaped this unusual world. And someday, perhaps within our lifetimes, perhaps within the lifetimes of children listening to these words, we'll detect another interstellar comet, and then another, and another. We'll begin to build up a population, a sample large enough that we can start to see patterns, to understand not just individual objects, but the overall distribution of comet types in the galaxy. We'll be able to say, with some confidence, what percentage of interstellar comets are water-dominated, what percentage are carbon dioxide-rich, like 3I Atlas, what percentage fall into categories we haven't even defined yet. This is the nature of exploration. You start with one data point, which is interesting but not conclusive. Then you get a second, which allows you to start making comparisons. Then a third. Then a fourth. And slowly, piece by piece, observation by observation, you build up a picture of reality that is richer, more detailed, more accurate than what you started with. This is how we learn. This is how we expand the boundaries of human knowledge. But there's something else happening here, something beyond the pure science, something that touches on why we do this at all. When we study objects like 3I Atlas, when we train our telescopes on a visitor from another star system, when we analyze its light and decode its composition and try to understand its history, we are engaging in an act of profound connection. We are reaching across the vast gulfs that separate star systems, across distances so immense that light itself takes years or centuries to traverse them, and we are touching, however briefly, however indirectly, another world. Think about that. 3I Atlas formed around a star we may never identify, in a planetary system we will almost certainly never visit. The conditions there, the temperature, the chemistry, the arrangement of planets, the history of that system, all of it is unknown to us and may remain unknown forever. But this small frozen world, this chunk of ancient ice and rock, made the journey. It traveled for billions of years through the darkness, through the endless night of interstellar space, until by chance, by the inexorable workings of gravity and celestial mechanics, its path intersected with ours. For a few brief months in the year 2025, humans and this ancient traveler shared the same small corner of the galaxy. We saw it. We studied it. We learned from it. And in doing so, we expanded our understanding not just of comets, but of the galaxy itself, of the processes that shape worlds, of the incredible diversity of environments that exist beyond our own cosmic neighborhood. This is why we study these objects, not just because they're scientifically interesting, though they are, not just because they challenge our models and force us to think more deeply, though they do, but because every new thing we learn about the universe, every mystery we solve, every question we answer, makes the cosmos a little less foreign, a little more comprehensible. It transforms the universe from an abstract concept, a collection of distant lights in the night sky, into something more concrete, more real, more connected to our own existence. We are made of star stuff, Carl Sagan famously said. The atoms in our bodies were forged in the nuclear furnaces of stars that lived and died before our solar system even formed. We are, quite literally, the universe made conscious, the cosmos waking up and beginning to understand itself. And when we study an object like 3I Atlas, when we determine its composition and trace its history and puzzle over its anomalies, we are continuing that grand project of cosmic self-discovery. The fact that 3I Atlas is not a water comet, that it defies our expectations and forces us to reconsider what we thought we knew, is not a failure of our understanding. It's an opportunity for growth. It's the universe teaching us, once again, that reality is richer than our imagination, that there are always new things to learn, new surprises waiting to be discovered. And that, perhaps more than anything else, is the message I hope you take from this story. The cosmos is not a static place. It's not a museum filled with objects that we can catalog and file away and consider understood. It's a living, dynamic, ever-changing arena where new discoveries are always possible, where every observation has the potential to reveal something unexpected. 3I Atlas came from the stars. It carries with it the chemical signature of another world, modified by billions of years of travel through the interstellar medium. It's dominated not by water, as we expected, but by carbon dioxide, transformed by radiation, shaped by processes we're only beginning to understand. It brightened unexpectedly. It accelerated in ways that puzzle us. It emitted nickel in unusual ratios. It behaved, in short, like the cosmic maverick it is, refusing to conform to our tidy categories and expectations. And that's exactly what makes it valuable. That's exactly what makes it worth studying, worth celebrating, worth sharing with anyone who will listen. Because every time the universe surprises us, every time we encounter something that doesn't fit, we have a choice. We can dismiss it, explain it away, force it into our existing frameworks, whether it fits or not. Or we can embrace it. We can let it challenge us. We can use it as an opportunity to expand our understanding, to refine our models, to grow. As 3I Atlas fades from view, as it continues its journey back into the depths of interstellar space, it leaves behind something precious. Data, measurements, observations, the raw material from which understanding is built. Scientists will study this comet for years, extracting insights, testing hypotheses, arguing over interpretations. Some mysteries will be solved, others will remain. And inevitably, the study of 3I Atlas will raise new questions we haven't even thought of yet. That's how science works. Every answer spawns new questions. Every solution reveals new puzzles. We never reach a point where we know everything. We simply continue to learn, to explore, to push back the boundaries of ignorance, one observation at a time. The next interstellar comet will come, maybe in a year, maybe in 5. We don't know when. But when it does, when another visitor from the stars passes through our solar system, we'll be ready. We'll have better instruments. We'll have more experience. We'll have learned from 3I Atlas, from 2I Borisov, from Oumuamua. And we'll discover new surprises, new anomalies, new things that force us to question and learn and grow. This is the grand adventure of science. This is the incredible privilege of living in an age when we have the technology to study these cosmic visitors, when we can point our telescopes at a distant speck of light and determine what it's made of, where it came from, how old it is. A century ago, this would have been impossible. 2 centuries ago, it would have been unimaginable. And yet here we are, in 2025, analyzing the composition of a comet that formed around another star billions of years ago, in a part of the galaxy we may never directly observe. It's not a water comet. It's a carbon dioxide comet transformed by radiation, carrying the signature of processes we're only beginning to understand. It's a reminder that the universe is vast and strange and wonderfully diverse. It's a message from the cosmos, written in the language of chemistry and physics, telling us that there is always more to learn, always new discoveries waiting beyond the horizon. And that, when you think about it, is perhaps the most exciting thing of all. No matter how much we learn, no matter how many questions we answer, the universe will always have more to teach us. There will always be another three-eyed atlas, another cosmic surprise, another opportunity to expand our understanding and marvel at the incredible complexity and beauty of the cosmos we inhabit. So the next time you look up at the night sky, remember this story. Remember that out there, invisible to the naked eye, there might be another visitor from the stars, another ancient traveler making its way through our solar system. And remember that scattered around the world on every continent, in observatories and universities and research centers, there are people dedicated to studying these visitors, to learning their secrets, to expanding human knowledge one observation at a time. They're doing it for all of us. They're doing it because the universe is calling, because there are mysteries to solve and questions to answer and wonders to discover. They're doing it because we are, all of us, citizens of the cosmos, children of the stars, explorers by nature and by necessity. And when they make a discovery, when they learn something new about an object like Three-Eye Atlas, when they share that knowledge with the world, they're inviting all of us to join them on this incredible journey of understanding. The comet that wasn't made of water has taught us more than we could have imagined. And somewhere out there, in the vast darkness between the stars, the next messenger is already on its way. What will it teach us? What surprises does it hold? What assumptions will it shatter? We don't know. We can't know. But we'll be watching. We'll be ready. And when it arrives, we'll learn something new about the universe we call home. That's the promise of exploration. That's the gift of curiosity. That's the endless, amazing adventure of science. And it's an adventure that belongs to all of us, if we choose to embrace it, to celebrate it, to let it fill us with the sense of wonder and possibility that drives the human spirit ever outward, ever upward toward the stars.